from the north, I'm from Erie. When I was young, I learned to really hate snow because I was the guy who had to shovel the snow every morning before I ate. Did not like that. Anyway, this is really a day where I want to do problems. Now, hopefully you've all had time to really try a lot of these different convolution problems. You can see that they can become difficult and challenging. That should be it should be very apparent to you. I want to do some problems at the end. If there's time today, I'm going to start discrete convolution, where we'll go into some discrete signal definitions. Right? But this convolution is challenging, especially with some of the more difficult functional forms. Now, does somebody have a specific question? By the way, did you get your book so I can have mine back?
Not yet. It's supposed to arrive today.
No, it's
later.
all right.
It's supposed to arrive in the mail.
She's borrowing my book at the moment, mainly to tilt that thing up. Yeah.
Oh, I just had a question about how often would we be expected to sketch graphs?
To what?
How often would we be expected to sketch graphs?
Well, you should be able to sketch the output, the y of t, after you convolve, for every function. You're always going to be expected to provide a sketch. A mathematical form in a sketch. They're not, most of the stuff is pretty apparent though. You have e to the minus t times u of t, it's pretty easy to do that. A sine is pretty easy to sketch. There's nothing really that complicated. The shark's tooth is the hardest one. It goes up and then down, but we'll do it. Now, do you have specific questions about the problems? Because I gave you a whole bunch, and I gave you the solutions, and I gave you some of the ones that were even, matter of fact, Ruth, I think you asked me if one was, I'm going to start with yours because this is the type of problem that you can expect. It's a bit more difficult because there's more things happening. So for this problem, I don't know the number of it, but it looks like this.
4.3b.
4 point what?
4.3b.
3, and this is part B. So for this one, boy, that's a good marker. For this one, it has a function that looks like this, where this is really going to be e to the minus quantity t minus 1 times u of t minus 1. And we'll call that x of t. And it has another function to convolve it with. And this function, unless I'm mistaken, looks like this. And this is u of 1 minus t, I believe is what they have.
1 plus t.
Oh, I'm sorry, 1 plus.
So it starts at
No. It can't be 1 plus t, can it? Because then it would be 0. See, it does this, right?
That's after you flip and
Oh,
shift
it's not, okay. My bad. So it actually is this, right? And that would be u of, now this is u of t minus 1 right there, right? Is this the one you're talking about?
The one that I had was,
Does it look like this before it's flipped and shifted?
it starts at -1, goes up and to the right.
Do you have it in front of you? Oh, okay. Then it is plus 1. My bad. What's this? All right, those are the two functions you have to. Now you can see neither one starts at 0. This is important. So it gets more complicated. And you have to have your head clear on this. And again, remember what convolution is the definition of. The convolution of x of t convolved with h of t, or really, h of t is actually an integral from minus infinity to infinity of x of tau times h of t minus tau d tau. Now, it doesn't matter which one of these functions, you can flip these. It can be h of tau times x of t minus tau. It doesn't matter. Convolution is one of those operations you don't care what the order is. So I tell everybody the function that has the most going on, you leave alone. Just looking at this, what has the most going on? That one, right? Exponential decay. Leave it alone. Now you simply replace t with tau. So this is going to become tau. this is tau, this is tau, and the axis is tau, and you just leave it alone. Next, you take this function, the first thing you do is flip it on the axis, right? So now, when we flip it on the axis, we get this, and that is going to be, if this is going to be h of t, this would be h of minus tau. Do you all agree with that? This axis is tau. Agree? And that's 1. Now you can see at this point t is 0, correct, class?
Mm-hmm.
T is 0 and it just begins to overlap, correct?
Mm-hmm.
So you can say right away the convolution of these two is 0 for t less than 0. Now the next part will be for t greater than 0. And here, it's important that you keep your head on straight on this one. All right. Now, what is this point here? Well, that is at 0, right? It's 1. But as t increases, this point is 1 plus t. Does everybody follow me on that? It's not just t, it's 1 plus t. It was already 1 at t equals 0, correct, class? Now you add that 1 to it. And now the curtain starts drawing this way. So, just to really expose this, now when I look at this, remember that point in the domain tau is 1 plus t. This is what you were asking about. You have to really focus. Believe me, this can get very confusing. Where is the area of overlap? Well, it's nice that this has a height of 1, I'll tell you that. Because now we take the product of this function times this function, right? And we can see really what we're left with is, since it's just 1 here, we're integrating this function from 1 to t plus 1 to get the convolution. Do you all agree with that, class? How many tried this one? All right. This is a very good problem. It really exposes a lot of the problems you have when things are not starting at 0. When you have two functions that both seem a little hard to get a handle on, you've got to choose one, and the one with the most going on, I say anything that's time varying, like this, that has a variable value, an exponential decay in this case, leave that one alone and flip the other one. Sometimes you can't. Sometimes you have to flip one that's got something like that going on, but it's better not to. So for this one, this is actually going to be, and I'll do the integral here, it'll be the integral from 1 to t plus 1 of that function up there, which is e to the minus tau minus 1, right, times d tau. This will be my convolution, y of t. Do you all agree with that? You all see? Now, remember, the integration is in tau. When you do this, you can pretty much say, well, this integration just breaks down to be e to the plus 1. Well, let me do it this way. I can take e to the minus 1 is plus 1, e to the 1 times the integral of e to the minus tau from 1 to t plus 1 d tau, and that's e to the 1, and then when we integrate this, we get minus e to the minus tau evaluated from 1 to t plus 1, and therefore you get e to the 1. I'm going to say this one time here. I'll probably say it a few more times. Whenever you see a minus sign there, and you got limits, flip the limits, get rid of the minus sign. That's my advice to you. Does everybody understand what I'm saying? You get rid of this minus sign, this becomes 1. This becomes 1 plus t. And then evaluate it, so I have e to the minus 1, minus, right, e to the minus quantity 1 plus t. That's the answer. If you want to, you can simplify it, multiply it through. If I have e to the 1 times e to the minus 1, I have 1, right? And then if I have e to the 1 times e to the quantity minus 1 plus t, right there, that's really going to be minus e to the minus t, and it would be times u of t, right? Because that's good for t greater than 0. Do you agree with me, class? And that would be the answer, I believe. Is that what the form of the book had?
Pretty sure.
I think it is, but I don't remember. All right. Now this right here, that's the correct answer. This is simplified. That's the only thing I've done. Everybody see this, class? It's very straightforward if you go through the steps I'm showing you, but it can be confusing as heck if you don't immerse yourself in this. And if you try cramming Thursday night for the Friday quiz, God help you. Really, I mean it, because this is pretty bizarre stuff. All right, now that's the problem I want to do. Do you have other problems? I had one person stop by and ask something about Dirac delta functions convolved and stuff. That was you. And I'm going to show you some properties of convolution, additional properties that are really self-evident, and I'm going to just expose them. Additional problems. Can everybody see the videos okay? How many have actually looked at the videos? I want to make sure, I would advise you to take a good look at those, and also, you know, you can post, ask questions on there, right? I encourage you to network like that, because everybody here's got a vested interest in figuring out how to do this. Some people are going to understand it quicker than others and can help others. And it is very good to do that. I'm going to level with you. It's one of the best things I've learned to do, is try to get social media on our side for a change and make sure that you can actually network and help each other in these courses. And it's valuable. All right, so next, what I want to do is go through some of the standard properties that are self-evident if you look at the definition, but sometimes you just need to see them. If you have a function x of t plus a function y of t, and you want to convolve it with some function, call it h of t, right? Well, you don't have to add these two together first and then do the convolution. You can say what this is really equal to is x of t convolved with h of t plus y of t convolved with h of t. That's the same thing. Follow me? So you can distribute this through here, just like you would in any kind of standard mathematical operation that's linear. Follow me? You can also do this. If you have something like this in a block diagram form, this just shows you the flow of the signal. If this is x of t, and I had some h1 of t here, h2 of t here, h3 of t here, h4 of t here. I'm going to box all these things. And then put a summer operation here. And this is my output. So this is going to be my y of t. Now when you look at this, I have two functions in series. All right? X of t here convolved with h1 of t would be the output right there. Convolved with h2 of t would be the output at this point. It would be x1 of t, and it would be convolved with h1 of t, and then that operation is convolved with h2 of t. That's at that point, correct? I think everybody sees this, but I have to make certain that everybody sees this. Right at this point here, it would be x of t, I'm sorry, I put x1, it's just x of t, and then that is convolved with h3 of t, and that whole thing is convolved with h4 of t, right? So now I'm just saying that's there. This is the symbol for summation. It's a summing operation. It means addition. And now if this had a minus sign there instead of a plus, then you would literally subtract this from this function. Do you follow me on this? So there's always going to be some designation, either a plus or a minus, to indicate whether you're adding or subtracting, but you are summing nevertheless. So out here, my y of t can be written as x of t convolved with h1 of t convolved with h2 of t added to x of t convolved with h3 of t convolved with h4 of t. And you all see I've just restated the obvious, right? Now, here's the thing about convolution that's nice. You see x appears in both of these. Y'all see that right there? If you want to factor x out, you can. You can factor x right out of there and just say, I'm going to take this plus this and then convolve it with x of t. And the order of operation doesn't matter here. It doesn't matter which one you have first. You know that when you have convolution. As a matter of fact, with convolution, if you have any function, let's call it x1 of t, convolved with x2 of t, convolved with x3 of t, and we could keep going. The order that you do convolution doesn't matter. If you want to convolve these two first, it's fine, and then convolve the product. If you wanted to convolve these two first, and then convolve it with x1, it's fine. And furthermore, if you wanted to convolve x1 and x3 first, and then convolve it with x2, that's fine also. So doesn't this remind you of any linear mathematical operation? If you have a times b times c, it doesn't matter if it's a times c and then times b, it doesn't matter the order. Everybody got that? It's the same with convolution. There were several problems that had well, at least one problem that had a block diagram showing you things. Now, there are also written statements about problems with convolution that use Dirac delta functions. I don't know the number on that one.
Yeah.
But this is a good question. The Dirac delta functions, or delta functions, are they're a gift because they're so easy to do the convolution. And I can't overstate this.
It was problem 2.15.
All right. I just want to say, I'm going to have to restate this. Make sure everybody's on the same page. You have to make sure you understand this. If you have any function, a delta function, and you have some t minus a is a constant, and you convolve that with any function f of t, what you actually get is just f of t minus a. Now, I think I did that in class once. I proved that. Do y'all remember that? How many do? If you don't, you can see it. It's very evident. If you take the definition of convolution, you say, I'm going to convolve two functions. One is going to be delta of t minus a convolved with f of t. Right? What I'm going to do is flip and I'm going to leave this one alone, so it would be f of tau. Then I'm going to take this and replace t with t minus tau. So now I have it's convolved with delta of quantity t minus tau minus a. And that would be integrated d tau, right? From minus infinity to infinity. Do you all see what I'm doing here? The definition of convolution, I'm using this function as the non-flipped one, and I'm flipping the delta. Got me? Now, pay attention. When does that delta function turn on? Well, it's when the argument here is 0, right? If you don't see it, by the way, don't make mistakes. Just write it out. Say t minus tau minus a equals 0, right? I want to know what tau, because the integration is tau, makes it 0, and you can see what? Tau would be equal to t minus a. You all see that? Everybody see it? Please watch this and make sure you see it. And if it's boring, you forgive me. But I have to make sure that you see this. All right. Now, that means one thing. This delta function is 0 for all time, but right there, right? I mean, for all tau, but right there, correct? So what I can do is, instead of this, I can say, this is going to be t minus a minus some epsilon, and epsilon is going to approach 0. So it's a very small neighborhood just below where the thing turns on. And then I can make this upper point t minus a plus epsilon. Again, just above the point where the delta function turns on. But that means this function, if you have f of tau plus or minus epsilon, right? Or plus or minus anything, it's about f of tau, right? And in this case, tau would be t minus a. So now I can take this out in front. It looks like a constant is what I'm getting at. And I can say this is really f of t minus a out in front. And you know that the integration of a delta function from Minus infinity to infinity, in our case, from just below where it turns on to just above where it turns on is 1, right? So therefore, you just get f of t minus that. That's why this works. Got it? Everybody? Now, when you convolve a delta function with anything, you find out where it turns on, and you replace the argument of the other function by this argument. Just take the argument and stick it in there. Everybody got that? Now, there's a problem in the book. You got to help me here.
Sure.
And
It was
u of t, right?
Mm-hmm.
And it's convolved with, and he's got a bunch of them. Delta t,
Mm-hmm.
Just delta t?
Just delta t, and then minus 3 delta of t minus 1, plus 2 delta of t minus 2.
All right. So they want the convolution of this. Now remember, I can distribute this. I could say it's the convolution of this times this, right? Minus the convolution of this times this, correct? Plus the convolution of this times the last one, correct? But anytime you convolve a delta function with anything, you just take the argument of that delta function and stick it in the argument of the function you convolved it with, right? Everybody see that? I'm sorry if I'm anyway. I hope this recording goes well here, because this is an important fact. So what is this going to be? It's going to be this. There's my function f of t. Happens to be u of t. I replace the argument with t, so it's u of t, right? Then there's a minus 3. 3 is a scale factor. It just scales it. It's a multiplier. Where does this delta function turn on? Minus 1, right? Take the argument t minus 1 and stick it in there. This is how simple it is. For the last one, it's going to be plus 2 of what? U of t minus 2. I mean, that's how simple that is. You got that, everybody? And that's the answer. Now, here's the trick. If I asked you to sketch this, this is where people, oh God, I never thought of that. Sketching it is important, so we're going to sketch it together. All right? When I take a look at this function, you'll notice that the function that turns on the first is u of t, and it turns on at t equals 0, correct, class?
Yes.
So if this is t, this is 0, it goes like this. It goes up to 1. The next function that turns on is this 3, minus 3 u of t minus 1, correct?
Yes.
And it goes down 3, right? So I was already at 1 when I hit 1, wherever that is. Now I go down 1, 2, 3, and I hit minus 2. And I stay there until I hit 2, correct, class? Mm-hmm. And at 2, it goes back up to 2 points, right, or 2 levels, 2 values, so it goes to 0, correct? And it looks like this. You asked me about a sketch. That's a sketch I'd expect you to be able to do accurately, all right? When I say accurately, there's 3 things you have to do right. Have you had Gross yet, Dr. Gross? Well, when you do, you have.
I have now.
Oh, he will drive you nuts with this. You have to label your axis. This is t, has to be labeled. The increments have to be shown, all right? And Gross will tell you even need the units here. All right? I'm not that picky. T is in seconds in our class, unless stated otherwise. Then on this vertical axis, it's unitless, unless I could put volts in there or something if I wanted. But basically, when you do an axis, you have to have a sketch where you label your axis. This is unitless here, and then you put to scale, rough scale, the actual increments when you do a sketch. Follow me on this? Because what I'll get is this. Something like that. And what do I do with that? You get no points, all right? You have to make an accurate sketch, not just something where, oh, he'll give me half a point for it. Because I don't give partial credit unless it's really deserving. You have to show me that you made a goof where, you know, for some dumb reason, you may come down 3, but it's an understandable mistake. You saw the minus 3 there, something like that. You can't just put something down and try to argue with me. Because, and believe me, I'm one of the more easy to get along with teachers. If you do this with Gross, you might start taking more points off. I even had one professor, I'll tell you this story. Remember, I'm from another era. Professors at that time were gods. So when anybody would go in to argue for points on a test, he would always make sure that he lowered them a letter grade, always. They can find things wrong, all right? And everybody kind of figured that out, so he never was bothered about exams, and I remember that very well. We call him Dr. F, by the way. All right. I had courses that half the class got Fs in. All right, they had to attenuate a certain number of students. This is at Penn State, back in the day when they had to admit all these students. So engineering was overcrowded, so how do they get rid of them? It's simple. You flunk out everybody below a certain threshold. All these people were flunking out, turning into business majors and stuff. And I'm not sure that's the fairest thing, but I'll tell you one thing. It changed the whole atmosphere in studying. Everybody studied all the time. I never went to a football game as an undergrad. Didn't have time. I basically, until I passed my doctoral qualifiers, didn't drink, didn't have any time to date or anything like that. The only thing we did was work. And it was survival, because it was vicious at that time. Pennsylvania's a big state. Penn State is a land grant. It's inexpensive. It's a very good education. If you got the money, you go to U of Penn, because that's an Ivy League. It's a very good college, but it's very expensive, all right? My father's blue collar. I didn't have that kind of money. Everybody that didn't have that kind of money is down there, and I've got guys that they're perfect SATs, perfect ACTs next to me in class. They should be at MIT. They're there, and you're in a fist fight with them, so to speak, for your grade. It really changes things. You are no longer relaxed. But anyway, that's from another era. Things have changed. So now, I covered my 2 points I wanted to. Do you have any other questions specific to the homework? There's a lot of homework. Yeah.
There was a function where it was a convolution of a pulse function with a triangle function together.
Sure. Do you remember the number?
There was one that you gave us,
Oh, yeah.
It was, yeah.
A pulse function?
Yes, sir.
So can I just put this down, P tau of T? Do you want, what's tau on this one?
2.
2.
Okay. All right, and it was convolved with a triangle?
Yes, sir.
And what's the width of the triangle?
2.
Oh, that's nice. All right, Elliot?
It was T minus 1.
Oh, this is T minus 1? So this triangle is offset. So let me draw them for you. We want to convolve these two functions. This is a pulse function, and it has a width of 2. And we want to convolve that with this function. This is a good problem. The triangle function is this. Has a height of 1, and this is a triangle function with 2 of T minus 1. We're going to convolve. Great problem. Now, can everybody see the triangle's got more going on, right? And there are 2 domains that you have to define what the function is, not just one, because it goes up, right? It's a ramp, and then it ramps down. So you have to be careful about the time frame. Are you with me on this, everyone? So now you carefully define it. This is a straight line. I think I did something like this earlier, didn't I? In class?
Yes.
All right, right here, you can see that for this straight line here, this is just going to be tau, right? Let's get rid of this right away. That's just tau, and that's good from 0 to 1, correct, class? Can you all see? I don't want to go, you all agree with me there? That's just tau? All right. Now, what is it right here?
Negative tau plus 2.
Well, it has a slope of minus tau, right? And the 0 intercept is at 2, correct? So when tau is 2, minus 2 would be the value of this, plus something, or plus 2 would make that 0. Do you agree with me? And that's what the functional form would be from 1 to 2. Agree? I always do this. I put an arrow and say what the mathematical function is that represents that. And then beyond 2, it's 0. Correct, class? All right, now we do the flip and shift. So this is tau. Now we put this down. And we flip this function, which doesn't change its character at all, but it looks like this, right? And this is P2 of minus tau. Can everybody see this? I'm going to slow down. I want to make sure I just flipped it around, right? Now, the thing is, this point here is 1, and this point is minus 1, correct? But I can see there's already overlap at 0, t equals 0, correct? So now what I'm going to do is move this back, and remember this point will be 1 plus t, and this is t minus 1. All right, that's the point. Let it be 0. Isn't it 1, right? If t is 0. I'm gonna move that back and let t equal minus 1. Follow me? So when t equals minus 1, it looks like this. This is still t plus 1, t minus 1, but this is going to be for t greater than, in this case, minus 1, and less than 0. In other words, I've taken the pulse function that was centered here, that had a width of 2, and I've moved it back so it starts at t equals minus 1. Now I'm going to let it roll through here from 0 to 1. Follow me? Can you all see this, guys? And we're going to get the convolution, which means when I look at this, it's basically this. And here's the area of overlap. Thank God that has a height 1. So it's 1 times this, right? And then we integrate that function. Do you all see this? But it's for this domain, only from minus 1 to 0, correct? So when we integrate this function, when we integrate tau, let me do this way. My y of t value will be the integral of tau d tau, in this case, from t plus 1, right? Because that's the low, from 0. From 0 to t plus 1, but the domain would be for t greater than minus 1 or equal to, and less than or equal to 0. Now when you do this integration, that's going to give me tau squared over 2, correct? Evaluated from the limits, or it's just going to be t plus 1 squared over 2. Do you all agree with me there? I've simply done the integration. The integration of tau d tau, let me finish it and I'll get to you. Tau d tau is going to be tau squared over 2, correct? Then you have to evaluate the limits. At 0, it's 0, correct? At t plus 1, it's just t plus 1 squared over 2. Go ahead.
How did you get the t plus 1 down?
Remember, what's this? That's the upper limit, right? The lower limit is 0, because this axis is tau. So the overlap starts at 0, and it goes to t plus 1. Take a good look.
Why couldn't it just be t?
Well, that wouldn't work, would it? Remember, the pulse function, if you put this limit for the pulse function out here, is what? At 0, it's 1 already, isn't it, class? Remember? Right? So we have to say this point is t plus 1, because when t is 0, it's already 1, right? Right? You all see this? It's real important you mess with these things. Yes, sir?
I was going to ask you, how can you shift t plus 1 to 1? That way the area is symmetric. Like instead of integrating between 0 and 1?
Well, the definition of convolution is this. It's the integral of whatever the functions are. And I'll just say this. It's the integral of x of tau times h of t minus tau d tau, right? Technically from minus infinity to infinity. But what we have is something with a finite duration, right? So we integrate and we look at where the overlap begins in the tau domain. It begins at 0, right? The lower limit is 0, and it ends at t plus 1. But t is limited from minus 1 to 0. So when t is minus 1, it just starts. Got me? Then the overlap begins. And then at 1, this is where all of a sudden we have to get a different version of the convolution integral, because now we've got that thing going the other way, right? We've got to add up. This gets a little tricky, so hang with me. So that's true. This is the answer right here for this domain. Now, just work with me on this one. Remember that we still got part of the boxcar out here. Now, when it's coming through between 0 and 1, now this boxcar is moving through, and from 1 to 2, the lower integration starts at 0, but the upper integration is going to stop somewhere up here. Can you all see this, class? All right, let me try to draw this for you. This is a good problem, by the way.
Would it, never mind.
So now we've got this going on. We've got the boxcar up here. The upper limit is still t plus 1, the lower limit t minus 1 there, but now the area of overlap is this. It's all of this, right, up to the point here where it's t plus 1. Can you all see that? Everybody? Yes?
I guess just a question, I guess. Why did you decide to stop there as well, like going from 0 to?
No, I've got to go from what? From 1, I've got to make sure I'm in this range, right? All right, now look, there's still part of the boxcar back here hasn't gotten up there. And I know it will get through there when t is equal to 1, right? Then the whole thing's in, right? Then I got a different integration. But right now, I've got to integrate from here to here, right? If you take a look, if the whole boxcar comes in here, then I go from 0 to 2, don't I?
Right.
But that would be just at 2, right? I mean, just at t equal 1, or which would be equivalent to this being the 2 point, right? Now, please watch this. And I'm going to level with you. I sat in your shoes, and I know this can be confusing. The trick to beating these things is spending a lot of time up front on this stuff. Not before the quiz, up front, like days before. And then if you have questions, you come see me or ask your friends on GroupMe or something like that. Don't wait till the night before. Then you get more confused because now you're scared that you're not going to figure it out. And it just feeds on confusion. It gets terrible. I'm trying to level with you guys as best I can. Remember, serious students really, they will always, I think, at least consider the advice given by the professor on how to deal with the course. This is not a course to take trivial. It will destroy you. It's a very conceptually difficult course unless you spend time up front. Now, you're all engineers, so you're all very bright, but I mean, mediocre students get creamed right here. This is how come engineers are paid so much, because they have to be very smart. You have to have the ability to not only be somebody who can memorize stuff, you have to see things, be creative, and be very good with inductive reasoning. I've always said people that are very good at chess are very good engineers, usually. And matter of fact, I had a kid, and I'm going to finish this thought, named Stephen Muhammad, who I didn't know at the time that he was a Federation master in chess, and came up to my office. And he's an African-American student, was in the military, absolutely brilliant. Very mild-mannered. I didn't know who he was. He had questions about ELEC. I was working with a grad student, but I had a chess program up because I play chess, and I'm not real good at it, but I enjoy it. And it was at the highest level, the grandmaster level. Has anybody ever used Chess Master in here? Anybody? You have? It's a good program. If you want to learn chess and put a grandmaster, you'll never beat it, I don't think. I mean, if you do, come see me. I've got a career for you. But anyway, it's at the highest level. And it wasn't Chess Master, it's equivalent to Chess Master, like a free version. And he comes in there and he looks, he's asking a question, and then, yeah, do this. And then I'm kind of ignoring him, helping the other grad student. And he says, oh, do you play chess? And then, yeah, I play chess once in a while. He goes, well, anytime you want to pull up a board, you play chess? Well, go ahead, have at it. So I'll keep him busy for a while. So after about 8 moves, I look over there, and he's got an advantage. I'm looking at him, and he beat the thing. Then I said, who are you? Because there's not a person in the state of Alabama who can beat that game as far as I knew. The thing was, he was the state champion, not only Alabama, but Tennessee and Florida. And he qualified high in the New York Open. Now he's the international master. I think he has 2 of his grandmaster norms, if you know what that means. So this guy is one of these people that was a very good engineer. Surprise, surprise. Anybody that's real good at chess usually is real good at engineering. Yeah?
So in essence, you need the integration between that point before you've reached 2. Does that make sense?
You have to take the product of these 2 functions, and the product is what you integrate. What I do is, because this is 1, the product is this. All right, I show you the product. That's what this is right here. I'm showing you the product visibly, but you have to integrate. All right? So now when we get to there, let me just get to this because I got a little talkative. So now, when you take a look at this, the lower integral starts at 1, but we have to stop it at 1. We're going to do this in 2 parts because that's where the function is clearly defined, right? It's just tau, d tau. But then we have to add the portion of the integration from 1 to t plus 1. So we have to go the integral from 1 to t plus 1 of, and this is going to be 2 minus tau d tau. Take a good look at that and make sure you see why I've done what I've done. You got that, everyone? Class? Now this is pretty easy to see. This one's straightforward, right? Tau squared over 2 from 0 to 1 is just 1/2, correct, class? So this is going to be 1/2. This one takes a little more doing. It's going to be plus, when I integrate 2 d tau, right, I get 2 tau. Then I have to put in the upper and lower limits. So I have 2, and then I get, this is just 2 d tau. Then it's going to be t plus 1 minus 1. Now I on purpose put this in brackets. This is supposed to be t plus 1 minus 1. Product, it's multiplied by 2. When I integrate minus tau, I get minus tau squared over 2, evaluated from 1 to t plus 1. Do you all agree with me there? Remember, this is only from t, in this case, it's going to be from 0 greater than t less than 1. Agreed, everyone, class? So when you do this, you can simplify this right here, because then you put the upper limit of t plus 1 squared over 2 minus just 1. So I can go ahead and say, I'm going to leave it like that. Do you all see me? We could simplify this in a bit. I'm pressed for time here. Only got about 4 minutes. Now that's true. This is true for 0 to 1, right? Keep watching me on this one. So now, when t equals 1, we're right here. I'm going to try to draw this. Now we're going to move beyond that. We're going to go for t greater than 1, less than 2. It's important you see this. So I'll put that over here. So it's going to be for t greater than 1, less than 2. The reason I made it less than 2 is this. You see, the boxcar's got this width, right? Now, right at 1, we're here, right? Now as it's moving through, all of a sudden the front end's gone, right? The product stops, the product thing, integration, the upper point is 2, but the bottom point is going to be t minus 1. You all see this? So now I've got to say, this is getting messy. So now, that's 1, that's 2. Now when I take a look at that, my boxcar is here for the next range. The area of overlap, or the range of overlap, is here. I hope you can appreciate this. Do you agree? This lower limit is t minus 1. Never changes. That's always the value. It's where it's located. Here it's in between, it's really between 0 and 1 in the tau domain. Correct, class? All right, this is a good one. So now, I'm just going to say this. If I'm looking at the integration from here to here, you all see that this area is there. It doesn't change. So just leave it as a half, right? Base times width divided by 2 for a triangle area, correct? So that's 1/2. I'm going to get that out in front. Now when I do this integration, just listen to me now because I'm trying to get from here to here, it's really tau integrated d tau, correct? That's tau squared over 2, correct? Evaluated from t minus 1 to 1. So I'm going to put that here. So I have, it's 1/2 plus tau squared, over 2, evaluated from t minus 1 to 1. I'm going to just leave it like that. That would be the integral in that range. Do you all agree with me? You can put in this one and fill it, but now keep letting the boxcar go. And as it moves through, for the final range, now that would be for t greater than 2, less than 3. Now just watch this. See, the width of both of these are 2, correct? So that means the final width has 4, right? It started at minus 1, right? It's going to stop at 3. Got me on that one? I know that. So take a look where the boxcar is now. Now the lower limit, t minus 1, is here between 1 and 2, right? And the area of overlap is just this junk right there. Can you all see that? Hey, wait a second, I got 5 more minutes. For some reason, I thought this class ended at 1:45 because I'm teaching another course that starts at 9:30, goes to 10:45. I got 5 more minutes, but I wanted to make sure, you all see what I'm doing here? All right, now I'm gonna tell you, it's real easy to get clumsy and all of a sudden lose focus and not do these integrations right. It's very easy to get bored or just fed up with them. You can't do that. You gotta stay focused. It's the only way to really survive this. So from 2 to 3, what happens? Now I have the integral from what? From t minus 1, right? To 2 of the function 2 minus tau, right? D tau. Can you all see this, class? Can you all do that integration? It should be effortless to most of you, but you can do that integration. Now the answer's in the book, correct, or in the solutions that I gave you, right? You say you don't know it?
I didn't see it in the homework that you gave online, because
Has anybody got left? Can you look online to see if that's not there, send me an email. Because is this a homework from the book or from?
this is from the slides directly.
Oh, that's from, I'll tell you where I got that. It's from MIT, a guy's name's Oppenheim, fantastic teacher of signals and systems. You should watch some of the stuff he has. Those are homework problems he provides. But this, what I'm doing here, I should have put the answer in. I thought it was there though. I'll check. When you do this integration, it's fairly straightforward. 2 d tau integrated is simply 2 tau from upper to lower, so you get 2, and then it would be 2 minus the quantity, t minus 1. That's the first part. Then minus tau d tau is minus tau squared over 2, correct? From here to here, so I get, it's going to be plus or minus tau squared over 2 from the lower t minus 1 to the upper 2. And I'll say this again, this part stays, you gotta have that, right? And it's added to this, correct, class? Now this is what I do. I flip these limits and put a plus there. So I make this t minus 1 and put that as 2. And then you do the evaluation. Y'all agree with me, class? And that's the answer, right? I'm going to forego simplifying so I can get one more problem, but that's the method that you do it. And I'll tell you, it will get irritating. When I was where you're at, I used, because some of these problems, I mean, these are sort of low-level kind of things. They're only a couple. When you get 3 or 4 functions you convolve and they're all moving through, you kind of get, spending an hour on one problem will drive you out of your mind, you know, and you got 10 of them. It's like, how am I going to get this done in a night? It used to drive me bananas, but these problems were irritating until you get the hang of them, and then you will breeze. I'm going to tell you that. There's like a point where, bang, I got this. Everybody with me? All right, I wanted to do one thing with discrete convolution. I didn't have much time to set this up, but everybody sees that when I say continuous time, it means time is a continuum, it never changes. The functional forms are defined for all time. For discrete time, they're defined at points, all right, at n, integer values of n, 0, 1, 2, and so forth. So I have to first expose you to the functions before I do the convolution, but they're not hard to understand. They're just like the functions that you had before, except now they're evaluated only at integer points. Well, let me give this to you. Yell at me if I go over. First function, as you might guess, is going to be a delta function. And the way they designate discrete time is with a bracket. Now, I don't like brackets, so if I put curly brackets there and put an n indicates it's discrete. Got me? And the value of this is just 1 for n equals 0, and it's 0 else. That should make sense. Remember the delta function? It had an area of 1, but its value was infinite only, or tending to infinity at t equals 0. Correct, class? This is discrete. That's the first one. The next is really the integration of this, and I mean summation in the discrete domain. I don't have time for a little chit chat on that one. But it's u of n, and you might gather what that is. It equals to 1 for n greater than or equal to 0, and it's 0 for n less than 0. But it's discrete. For the record, this one looks like this. Here, n would go this way, be 0, 1, 2, 3, and so forth. It would just have a height of 1. That's the way they show delta functions, like that. All right. This one is just like u of t, only at discrete time points. So here, if this is 0, 1, this is 2, 3, it's this. At -1, it's 0. At -2, it's 0. Here, it goes to a value of 1, and they show these with stem plots, they're called. MATLAB has these. And it just keeps going on and on. It's one. Can you all see this? It's not hard to understand. It's discrete now. Big difference is, remember, the height of this is 1. It's not infinite. The area is 1. All right, that's the thing. The next function, and we can keep going on and on about this, I'll just tell you, it's n u of n. And this would be equivalent to the ramp function. And can you all guess what that is? Thank you. It starts at 0, right? And just take a straight line up there and start picking off points. 1, 2, 3, 4. It just goes up by n. That's it. Got me? And last thing I'm going to tell you with these, does anybody have a class in Park or something like that? Yeah, you do. All right. I'll stop. I'm going to tell you, I'm going to go through discrete convolution on Friday, start the class, but I'd like you to really take a swing at all these problems, and if there's something you don't understand, or that answer isn't available, something like that, come and there'll be a about 10-minute quiz at the end of class. If you know what you're doing, you kill it. If you don't know what you're doing, you probably we close. I usually make at least 2 quizzes up so we get, your neighbor does not have your quiz, is what I'm saying. I've had problems with some people looking on other quizzes. All right? Thank you. Can you check and see if that's